All right. Hi again, everybody. Happy Monday. I hope everybody had a good weekend. This will be my second attempt at teaching you via YouTube. I hope the first one was at least somewhat helpful, and I hope this one is even better, but we'll see. Today I'm going to do three things. I'm going to start with drawing some examples of physics diagrams of two forces working either with each other or against each other on the same object. So in this example, I think it's going to be similar to questions number 6 and 7 in the learning set. After that, I'm going to run through an example of calculating acceleration using Newton's second law, sigma F equals ma, or the sum of the forces on an object are equal to the mass of the object multiplied by its acceleration. Okay, and that should be similar to question number 16 in the learning set. And then finally, I'll wrap up with an example on weighing things in newtons, and that one will be similar to question number 19 in the learning set. So if you've done those questions already, that's great. Compare my work to yours. Make sure you're doing things correctly. If you haven't done them yet, follow along. Steal ideas and techniques from this video. Feel free to rewatch it, pause it, rewind it, whatever on your own time. Okay, so let's start with number 1. Okay, so let's start with our first example. Here we have two stick figures pushing and pulling a heavy box. They are working together, although they don't seem to like each other very much. So we're going to go ahead and do a force diagram for representing the forces on the box. So this will be a physics diagram, and as with every physics diagram in this unit, it's going to be a free body diagram. Before we get started, though, let's flush out the reality sketch a little bit. Let's give these people names. I'm going to call this person A, and I'm going to make up a value. Let's say they're pushing with a force of 75 newtons, and over here we have person B pushing with a force of 50 newtons. Okay, so this is very similar to question number 6 in the learning set, I believe. Now, as with every free body diagram, start with a dot. That's going to represent the object of interest. In this case, it's the box, the heavy box. In this case also, I think it's a good idea to make the dot a little bit bigger, and you'll see why in a split second. Now, we want to draw vector arrows to represent the forces on the box. A really key point with vector arrows is that the length of the arrow should be proportional to the amount of force on the object. Here's what I mean by that. Person A is pulling the box. So this vector arrow is going to be the force of A on the box, okay? And that's equal to 75 newtons, okay? And similarly, person B is pushing in the same direction, okay? In the same direction, but only with a force of 50 newtons. So I'm going to make person B's force vector arrow shorter, roughly 2/3 of the length of person A's force vector arrow. So the force of person B on the box is equal to 50 newtons. And of course, a good habit to get into is setting a positive direction for the problem. So there it is. That's a complete physics diagram, a complete free body diagram for two forces acting in the same direction. Now, I can't remember if the problem asked you to do this, but I'm going to go ahead and add up, find the sum of the forces. So the sum of the forces, that would be sigma F, is going to be equal to the force of person A on the box plus the force of person B on the box. Okay? And then you can go ahead and fill that in. So these would be my calculations. And the force of person A on the box is a positive 75 newtons, or 75 newtons in the positive direction, and the force of person B on the box is a positive 50 newtons. So that's going to be equal to a total force of positive 125 newtons, or 125 newtons to the right. Okay, let's go ahead and turn the problem around a little bit, and let's pretend that those two people are pushing against each other. Same thing. So I'm going to go ahead and add some numbers here. I think we said, what was this? B is in green and A is in blue. So person B is 50 newtons. Person A is 75 newtons. So we're going to go down here and do our free body diagram, our physics diagram. We'll start with a dot representing the box. Okay. Label it. Let's set a positive direction. Whoops. There we go. Let's set a positive direction, and let's go ahead and put in our vector arrows. Now force A, notice he's pushing that way, and force B is pushing that way. So let's put A's arrow on this side, and it's long because he's pushing with more strength. So force A on box, okay, is equal to 75 newtons, and force B on the box is shorter, okay, and that's equal to 50 newtons. There's our free body diagram. That wasn't too hard. Let's go ahead and find the sum of all the forces. So if I go over here, let's see, I'm going to go ahead and say that sigma F, okay, so these will be my calculations are going to say that sigma F is the sum of the forces, right? So we have, that's going to be equal to force A on box plus force of person B on the box. Well, the force of person A on the box is going to be equal to 75 newtons, but here's the kicker, it's in the negative direction. See, it's in the negative direction, so that's negative 75 newtons, plus the force of B on the box, which is a positive 50 newtons, because that person is pushing to the right. All right, so you add these together, and that's going to be equal to a negative 25 newtons. Now, the negative only matters in that it tells us the direction, so it's going to be 25 newtons to the left. Okay? The box is going to move to the left. The person A is stronger and will win. Okay, I hope those examples have been helpful. Let's go ahead and move on to another problem. Let's assume that we're lowering a bucket down to the ground. But as we're lowering it, maybe we're lowering it way too quickly and we slow it down. So it has negative acceleration. It slows down so that we can set it down gently on the ground. So here's our bucket. All right, this would be our reality sketch. And the bucket is going down towards the ground. All right, but it's showing negative acceleration. It's slowing down as it approaches the ground. So I'm going to go ahead and set up some room here for a physics diagram. In this case, it might be a good idea to have two physics diagrams. The first one would show the bucket slowing down, so it's going to be a motion diagram. So it's going really fast at first, and then the velocity is decreasing, so my dots showing velocity are going to get closer together. Okay, so this is going to be initial position and let's see, final position here. And that's all. Just a real quick glimpse to show that it's showing negative acceleration. Now, the more important one, though, would be our free body diagram. So I'm going to have a dot representing the bucket, and I need to show the forces acting on the bucket. Now, it is accelerating, so you know the forces are not balanced. What are the forces acting on this bucket? Well, we're going to have one force going down. That's going to be the force of gravity on the bucket. I'll say G on B. And we're going to have one force going up, which is going to be the force of the rope on the bucket. Now, which is winning? Well, it's moving down. So let's say that it's moving in the, we can make down the positive direction, I don't care. But it's accelerating up, okay? So it's accelerating up. That means that the force of the rope on the bucket is actually bigger than the force of gravity on the bucket. It's slowly winning, and given enough time, that bucket would completely come to a rest and maybe even begin to accelerate and move upwards. So I'm going to draw a larger arrow going up. Okay, you can see how the forces are not balanced, and I'm going to label this as the force of the rope on the bucket. Okay, oh, and it's also important to label the bucket as B. All right, and there it is. Maybe in your physics diagram, go ahead and set a positive direction. We're not going to do any math here, so it doesn't actually matter. But that's a good free body diagram right there. All right, let's continue on to the next problem. Similar problem. In this case, a person is pushing a big pile of rocks. Fortunately, there are wheels. So there's going to be acceleration here. I think this would be similar to question number 16, which asks what is the acceleration. So let's go ahead and say that this person is pushing with, I'm just going to make up a number, I don't know, 200 newtons of force. Okay? They're pushing with 200 newtons of force. The rocks have a mass of 1,000 kilograms, and then we want to know what is the acceleration. Okay? What's the acceleration of the rocks? And if you get the free body diagram, then the calculations are actually pretty easy. So here we go. Physics diagram. It's in the horizontal. There's one object. That's going to be the rocks. So I'll call it R. And there's the force of the person on the rocks. So force of P on R. And let's set a positive direction. And that's it. Okay, you can maybe say that that's equal to 200 newtons. And you can say that the mass of R, mass of the rocks, is equal to 1,000 kilograms. Done. Let's go ahead over here and use our physics rule. The physics rule for this is Newton's second law, sigma F is equal to ma. That's going to be the force on the rocks. The sum of the forces on the rocks is equal to the mass of the rocks times the acceleration of the rocks. We know the sum of the forces on the rocks because there's only one force. That's going to be, so calculations, 200 newtons are equal to 1,000 kilograms times A. All right, and now we can just solve. So the acceleration of the rocks, A sub R, is equal to what? 200 newtons over 1,000 kilograms. Let's see, yeah, that's right. So the acceleration of the rocks is equal to 0.2. And that's going to be meters per second, units of acceleration. All right, now this video is starting to get a little bit longer than I intended, so I'm going to hurry up and rush through the next problem. Again, feel free to rewatch the video on your own time. So the final problem, I think this is similar to number 19 in the learning set, is a problem about weighing things or weighing yourself. So let's say a stick figure steps on the scale and they weigh 700 newtons. Now, we don't really know what 700 newtons means because we grew up learning things in pounds, but let's figure out what that person's mass is. So here's my reality sketch. Now, in this case, we're going to need a free body diagram, so I'll do that over here. My physics diagram is going to be a dot. That's going to represent the person, so I'll name them U. And what are the forces acting on the person? Well, we do know that there's no acceleration here, which means that the forces are balanced. Does that make sense? The forces are balanced. So the forces on you are going to be obviously the force of gravity. So we have the force of G on you. And for every force, there's a force of equal magnitude in the opposite direction, pushing back. And that's going to be the force of the scale. And now because you're at rest on the scale, these two forces are going to be the same. Therefore, the two vector arrows are going to be the same length. So that's going to be the force of the scale pushing back up on you. And there it is. You can set a positive direction. Okay. And I think that should be complete. Now, you know the force of these two. You can go ahead and put in the values, 700 newtons. This is going to be equal to 700 newtons. All right. Okay, so since this is a weight problem, our physics rule is going to be our weight is equal to our mass times acceleration due to gravity. Our weight in this case, we know. Remember, weight is measured as a force. That's the force of gravity on an object. So this can be 700 newtons is equal to your mass, or at least U's mass,